Welcome to the exercises for Chapter 5. This chapter focuses on differentiation, the foundations of differentiation, what it means, how to interpret it, and so on. In this first exercise, we are going to explore what I call local slopes. These are slopes of line segments that are going to vary in length. And basically, the conceptual idea is that as the locality of these slopes increases, in other words, as the x-axis resolution increases, then the sequence of local slopes becomes the derivative. Okay, so there's a couple of parts to this exercise. I will go through the first part first, and then show you the results in code, and then I'll come back to the book to explain the later parts of this exercise. So to begin, we want to basically create this figure here. So what we are looking at here in this figure is the function f of x equals x squared with 5 x-axis points spaced between -1 and 5. So that's what you see here, -1 to 5. And there are 1, 2, 3, 4, 5 points between these two x-axis values. Now, this actually creates 4 line segments that are defined by the transition from each successive point. Okay, and when you do this, I encourage you to write this in a for loop, to implement this in a for loop. And then you want to write code to calculate the local slopes, the slope of each line segment, and generate a figure like panel B. So here we see the x-axis, same as over here. And now these horizontal lines indicate the slope of each of these line segments. So this line segment over here has a slope of, whatever this is, 8 point something. And this line segment over here, it's the second line segment in this plot, and its slope is, whatever this is, 2.5, I don't know. And here we see, this goes down a little bit. I hope you can see that. It goes down slightly. So this has a little bit of a negative slope. And that's what you see here. This is like minus 0.3 or whatever. So first I'll show you my code to create this figure, and then we'll come back and work through the rest of this exercise. Here I define the x-axis grid. Here I define the function y equals x squared. And here I'm plotting the function. So far, pretty straightforward. And now here is the for loop where I'm looping over all of the line segments and then calculating the slope and plotting the slope. So here I'm looping over 1 to n, right? So we have n points, which gives us n minus 1 line segments. So I'm starting to calculate at an index of 1 and not at the starting index of 0. Okay, so here I call this variable m for the slopes. And let's see, so I'm actually calculating the slope across 2 separate lines of code for reasons that I will explain later when I go back to the book text. So here I'm saying the slope here is this current value of y minus the previous value of y. So that's the change in the y-axis. And then I say that the slope value equals itself divided by the change in the x-axis. Okay, and then I'm just plotting that into the second subplot. You can see it's the x coordinates and the slope on the y-axis. All right, so I hope that makes sense. Pretty straightforward, I think, so far. Now that you have the code to create this figure, you can explore some parameters in this code. So one thing we want to do is experiment with the n parameter, which is the number of points in this function, which of course determines the number of line segments. And in particular, what I want you to pay attention to is whether the number of points in this function changes the behavior that we see in panel B, in particular the numerical values. Of course, there's going to be more horizontal lines as we increase n, but the question is whether these values on the y-axis are changing. Okay, and then the second thing that we are going to explore is to modify the code to basically remove the scaling by x, right? So the definition of a slope of a line is the change in the y-axis divided by the change in the x-axis. And now what we are going to do in the code is remove the scaling by the x-axis, right? So we're only going to quantify the change in the y-axis. And then we are going to repeat this experiment here where we're varying the number of points to see what happens with the behavior of this function over here and also the y-axis values. So let me see. So here the values go roughly from 0 to 8, and it looks like it's just a straight line going up. Okay, those are the two observations. Now I'm going to make this n equals 50. And here, let's see what those two values still look like, or those two observations still look like. So we still see it looks like a straight line, and it's still going from, okay, before it was at a little bit below 0, and here it goes from -2 up to above 8, so up to around 10. So it does look like the range over here is a little bit larger compared to n equals 5. Let's try n equals 500, and let's see how this looks. Again, the idea, now this looks like a straight line, but it's a bunch of dots here, right? The idea is that we are calculating all of these slopes between individual line segments. But now when I increase the number of points, the number of line segments increases, although I haven't changed the entire range or the domain of this x-axis here. Okay, so now we no longer see the individual horizontal lines. It looks like one thick line, but this actually comprises 500 individual line, or actually 499, right? Because we have 500 points, so there's 499 line segments. Anyway, we still see that it goes from -2 up to 10, and it looks like a straight line. Okay, so the conclusion here is that for very small n, we do see some differences in the slope values, but they're not very, it's mostly the same. When we change the n parameter, the characteristics and the values of the segment slopes is basically the same, except when we get to the low end of extremely few points, only 5. Okay, so next what I want to do is, let's see, I'll go back to 5 here, and now I'm going to comment this line. I should actually say comment here. So now this was the second thing we want to experiment with. Now we are calculating. It's no longer really formally correct to call these slopes. They're not really slopes anymore, but it is the change in the y-axis, and we're removing the scaling by the x-axis resolution. Okay, so now let's plot this again. Now the function itself doesn't change, right? The function is the same, but remember before when I had the x-axis scaling, this went up to 8, right? So the final segment slope was somewhere around 8 or a little bit above 8. And now it's, maybe around 13 or something. So let's see what happens when we go back to 50. And now what we see is the overall shape of this function looks the same. So it's still a straight line going up. That looks very similar to before. But now the axis value is completely changed, right? So now we're going from like -2.5 up to 1. Remember, with the x-axis scaling, it was going up to 10. Okay, and now I'll try 500. You can probably guess what's going to happen here. The values on the y-axis are even smaller. So now we're going from -0.02 up to, a little bit above 0.11, basically is where we are here. But again, the shape of this function is still the same. It's always the same shape of the function, which is a straight line going up. It's not trivial that it's always going to be a straight line going up. That's just because of the function x squared. But importantly, for any resolution for x squared, it's always going to be a straight line going up. But the y-axis values change completely if we remove this scaling parameter. Now, this is kind of trivial. It's a little bit obvious. But this is an important thing to point out because this is related to how we define the derivative and how we work with and scale the derivative of a function. In exercise 2 of chapter 5, we will explore comparing the analytic derivative of a function with an empirical derivative of that function, which is also called numerical differences. So that basically involves approximating a derivative empirically based on the function values, as opposed to analytically computing the exact derivative based on principles of calculus that you learned about in this chapter. Okay, so in particular, we are going to be working with the function x cubed minus x squared. And we're doing this all in NumPy. We're not using SciPy or SymPy here because we want to get numerical approximations and not the exact answer that we would get from SymPy. Okay, so implement the function f of x equals x cubed minus x squared in NumPy using 10 x-axis points linearly spaced between -1 and +1. Then you want to compute the derivative of this function, and we want two versions of this derivative. First is the analytic derivative, and that means that you differentiate this function on your own by hand, or maybe you can do it in your head. It's not so difficult. And then you implement that derivative as a function in NumPy. Second, you calculate the empirical derivative or numerical differences by calculating delta y by delta x. This is very similar to what we did in the previous exercise looking at local slopes. Now, in principle, these should be exactly the same, right? In fact, the definition of the derivative is exactly this, as delta x goes to 0. So, in principle, the analytic and empirical derivatives of this function should be identical. But when you make a plot of them, you see here's the function in the left, and here we see the two calculations of the derivative. We have the analytical derivative in black, and we know that that is correct because we solved it analytically uh, versus the empirical, the numerical approximation. And I don't know, what do you think about this? It's like, doesn't really look terrible. It kind of gets the basic shape, right? But obviously, there's a pretty clear visual mismatch between these two derivatives. Okay, so I have a lot more to discuss about why these are different and what to do about that. But first, I'm going to switch to Python and just get this far. So here I define the x-axis grid, -1 to +1 in 10 steps. And here I'm creating a separate variable called dx. This is delta x. It's the change or the grid resolution on the x-axis. And I'm just defining this variable for convenience, so I don't need to keep writing this out throughout the rest of the code. Okay, so here is the function. Here is the analytic derivative, right? So we apply the power rule. We take this exponent and we bring it down as a coefficient and we knock off 1. And same thing here. So that gives us the analytic, the exact function of the derivative, which is 3x squared minus 2x. And here is where I calculate the empirical derivative, and that is numpy.diff. So for the differences, but you could also, you don't even need this function. You could literally just write it out. The function values for each one minus the previous, and then divided by dx. Okay, and then make the plot. So here I'm plotting the function, here I'm plotting the two derivatives. Okay, now a couple of things to notice. The first is that we get an error message. Why do we get an error message? Well, panel A plotted fine. So the error message wasn't related to that. Panel B plotted, but it didn't finish the plot. So it crashed on one piece of the code for generating this plot. And in particular, it failed on this line up here, where I'm plotting the empirical derivative, the numerical difference. So let's look at the error message. The error message is x and y for plotting must have the same first mention. So basically, the number of elements mismatches. Okay, so in x, we have 10 elements, and in y, we have only 9 elements. Now, why do we have only 9 elements in the empirical derivative here? Well, that's because we are calculating the differences between each point and the previous point, right? So we're going to end up with 1 point fewer compared to the number of points in the function, exactly the same as how in the first exercise we had 5 points in the function, but only 4 line segments connecting them, and therefore 4 mini slope values or local slope values. Okay, so how do we solve this? Well, here I offer 2 suggestions. You can set the x grid, that's a variable that I'm using here for plotting the empirical derivative. You can set that to be, basically just one element less in x. It can be the beginning to the end, or the second point, the beginning to the end minus 1, or the second point to the end. Here I'm showing another option that I will discuss in a moment of averaging each successive point. So then the points in the middle will be the average. Let's see how this one looks. Okay, so first thing to note is that the plot now runs, the code runs, we get a plot. And yeah, this is what I discussed in the in the chapter, that there appears to be a mismatch, or there's obviously a mismatch there. Okay, so now we can try again, setting x to be the average, right? So this is the first to the penultimate point plus the second to the final point, and then divide by 2 to get the average. Now, on initial visual inspection, this does look a lot closer. This looks better. Here is the heart of the issue. The heart of the issue is that when we have a numerical difference, an empirical derivative, there is no true x-axis value, or no unique x-axis value that corresponds to each individual slope. That's because we are calculating the slope between this point and this point. And so which x-axis value do we use? Do we plot it based on this point or based on this point? Here I'm plotting based on the average of these 2 points. Now that seems very sensible. It seems like the right thing to do. The issue with that is a little bit more kind of conceptual, theoretical than practical, which is that when I choose to plot this empirical derivative as the average, that means that I am interpolating this function. I'm making up a data point here. I don't actually know what this data point is in the derivative, because I have not evaluated the derivative, the true derivative function, at this x-axis value. I'm just guessing, right? I'm guessing that the derivative at this x-axis value would look like this. Now, for this particular function, that assumption, that guess, that interpolation is really accurate. It works really well because this function is relatively smooth. The function and the derivative don't change that much relative to the x-axis resolution. But it's not trivial that it's going to look this good. It's also not trivial that it's going to be pretty accurate like this. It's just, yeah, it's a property of this specific example. So that's what I discussed here in the book text. So given a difference of y2 minus y1, is the corresponding x value y2 or, x1, x2 or x1? They're both misaligned, so they're equally correct and equally incorrect. Okay, so here I discuss a little bit more about this issue in some more detail. Here I present an alternative formulation for calculating the derivative, which is basically, instead of each particular point minus the previous point, we are shifting from each point in x, shifting a little bit back and a little bit forward. So minus h and plus h. And then, of course, we scale by 2h. I have not implemented this in the code. It's not specifically part of the instructions for this exercise, but if you find this interesting, of course, you can add a little bit more code to this exercise to calculate this numerical difference and see how that corresponds to the analytic derivative that you see in the plot. Okay, but the important point is this. As h gets smaller, which it means delta x, which means the resolution of the x-axis grid is getting smaller, so we have more points that we're evaluating in the function. All of these different ways of formulating the derivative and also choosing which x-axis value to plot, they all converge to the true analytic derivative. So as you increase the number of points that you're sampling in the function, these discrepancies that we see in the plot will get smaller and smaller and smaller until we get to a point where they don't actually matter. The final thing I want to do in this for this exercise is to change the n value, so the number of points that we are sampling in this function, and hopefully we will see that the empirical and analytic derivatives will match closer and closer. So to start with, I'm actually going to go back to how this was before, like this. And let me see, I think this is what I want to plot. Yeah, so just, encode in your visual working memory approximately the magnitude between these differences here. And now what I'm going to do is increase n, let's say, to 100. Okay, and now what we see is that they're still different, right? Visually, it's still pretty clear that the analytic and the empirical derivatives are not identical, but I'm sure you agree that they are much closer to each other now than they were with n equals 10. And again, we can try this with n equals 1,000, and by this point, it's probably good to, let me see, get rid of, just make these lines. Let's see, I'll make this one a red line just instead of the markers. Okay, now these are technically different from each other. These lines still technically do not perfectly overlap. And if you like, you can zoom in to the graph or inspect the difference between these two lines. But I think you see where this is going. We're increasing the x-axis resolution without changing anything else, right? I haven't changed any of this code. And now simply by increasing the resolution, we are getting a much closer, more accurate match between the empirical or the numerical and the analytic derivative. Exercise 3 of chapter 5 follows directly from exercise 2. So make sure you have solved exercise 2 before working through this one. So you will remember that at the end of the previous exercise, I encouraged you to play around with the number of points parameter. And what we observed there is that the larger n, so the more points we have to evaluate the function, the closer the match, at least visually, between the empirical and the analytic derivatives. So in that exercise, we just kind of, there was a bit of informal just playing around. So now what we're going to do in exercise 3 is investigate this relationship a little bit more quantitatively. In particular, what you want to do is calculate something called the root mean square error between the numerical difference and the analytic derivative. Here's the formula for root mean square. You can see, let's see, so the important parts here are we are calculating the difference between these two functions. So we have the estimate and the analytic function, or the empirical, the numerical approximation of the derivative and the actual analytic exact derivative. So we take the differences. Now, we don't really care if those differences are positive or negative. We just want to know what is the magnitude of the discrepancy. So that's why we square each of these differences. And now there's lots of points, of course, so we loop through, we sum over all of the points, and then we divide by n to give us an average. So that's where the mean comes from. And then, the s is for squaring. And then we take the root of that, so the square root of that result, and that just brings it down a little bit. Okay, so you want to compute that for a range of n parameters from 10 to 300. So what does the RMS, the root mean square error, look like when we have 10 data points versus 50 data points versus 300 data points? And you're going to get a plot that looks something like this. Here is the values of n that I'm going to use, ranging from 10 to 300. Here I'm initializing the output, and here's where I run the experiment. Now, all of this code here is literally copy-pasted from the previous exercise, so I'm not going to explain this in any detail. Here is the implementation of the root mean squared error. So we have the square root, and then we have the mean, and then we have the differences squared. Now, as we discovered in the previous exercise, the analytic derivative and the empirical derivative, or numerical approximation, have different lengths. In particular, the analytic, or the exact derivative, has n points, whereas the empirical version has n minus 1 points. So there's a few different ways you can deal with that discrepancy. But the way I did it here is by only considering the first n minus 1 points from the analytic function. Okay, so, and then after that, we just generate a plot. Fairly straightforward there. Okay, so what do we see? Well, we see that the errors fall down quickly, and they converge to 0. At the limit, when n goes to infinity, we have an infinite number of points. Now, it's not something we can do in NumPy, but in theory, that's the theory of differentiation. As the number of points goes to infinity, then the x-axis resolution of this function here, the x-axis resolution goes from delta x, which is, in this case, zero point 0.1 or whatever it is, it goes down to, I guess it's closer to zero point 0.2. But anyway, goes down to infinitesimal. It goes down to some number that is arbitrarily close to 0. And then we get the derivative. So there is like a theoretical conceptual world out there where eventually this function touches 0. But certainly you see that it decreases. Now, the rate at which it decreases and the exact value that it gets to, that depends on the characteristics of the function. But what is definitely always going to happen is that the larger n, so the finer we are sampling the x-axis grid, the better the numerical approximation will be to the true analytic derivative. That becomes really important for working with applications of calculus when you are measuring data or you have data or functions that are not characterized by a mathematical formula, but instead you just have a collection of data points that you measure or evaluate. Okay, very good. I hope that was interesting and sensible and insightful. The last thing to show here is just, to increase the number. So from 300, here I'm showing 100,000. Now, thing is, if you run all of this code for like 100, some really big number like this code is going to take absolutely forever to run. And the plot is just going to look messy. So basically all I've done is isolate one iteration, one calculation from this for loop for just one specific number of elements. And then here you can see the error is 0.5. So we can compare that with 300. And here you see the error is 0.01. So the error is falling by orders of magnitude as we increase the number of points here. The goal of exercise 4 in chapter 5 is to use SymPy to calculate the exact derivative formulas for different functions. This is different from using NumPy to approximate empirical derivatives, as we've been doing in the past several exercises. Okay, so there's a couple of parts to this exercise, or two parts to this exercise. I will start with the first part and then show you the solution and then come back to the book to discuss the second part. So the first part is to implement these functions here in SymPy and then calculate their derivatives. So here's one function. F of x is 5x over 4 plus 9 over 4. Now, you don't implement this. You want SymPy to calculate this derivative, right? So this is one function. Here's another function, x cubed minus x squared. That should look familiar from a few exercises ago. Then we have a third function, square root of x plus cosine of x. And finally, the function e to the x. So again, you implement these four functions in SymPy and then have SymPy calculate the analytic derivative and then print out the analytic derivative, or print out both the function and its derivative in pairs as you see here. There are many correct ways to solve this exercise. What I chose to do here is to create a list in which each element of the list is a symbolic expression for the function. So I'll talk about this in a moment, simplify. But here you can see x cubed minus x squared. This is cosine plus square root of x. And here we have e to the x. And then inside this for loop, over these different functions, these different elements of this Python list, I am calculating the derivative using SymPy, and then just printing out the function and printing out its derivative. All right, so that you see here. Now, what I would like you to notice is that this number is 9 divided by 4. It prints out as 9/4, and this prints out as 5/4. If I didn't use simplify, and I just put in 5 divided by 4 like this, then the output would be 1.25. Now, in some sense, 1.25 is the same thing as 5 divided by 4, but there are situations in SymPy where you will want to be able to represent both visually and also symbolically numbers as a fraction instead of as a floating point number like this. So that is where the function simplify comes in. So we're basically transforming this from a number into a symbolic representation of a number. So that is a little bit differently represented in SymPy. Now you can also do this for the numerator. That's fine. It turns out as long as you do it for one of these, then SymPy will represent this number as a fraction with symbolic numbers instead of the actual floating point numbers. The next part of this exercise is just to give you a little bit more familiarity with using the subs method on a symbolic object. So in particular, what you want to do is evaluate evaluate one function for three different numerical values of x and print out the results like this. So we have f prime, so it's the derivative of e to the x, but it's also e to the x of -1 and 0 and 2. And what you see here is that there are two results being shown. There is the symbolic result, and then I'm saying, so that is an exact equality. And then I'm saying is approximately equal to this number here, which is not the same as e to the -1. This is a numerical approximation. It is e to the -1, just written out to whatever that is, 6 numbers after the decimal point. Okay, and basically the purpose here is just to give you a little bit more experience working with the subs method, working with SymPy expressions and LaTeX printing and so on. And that code you see here, so I'm evaluating these points. And here I'm just saying, let's see, so printing out the function derivative at this value, this numerical value here, which is going to be point P. So that's, these three values here equals, and then I have the second string interpolation, which is literally just substituting in for x, the value of P. And then I'm saying it's approximately equal to this value. Notice here I have %s for interpolating a string or replacing with a string, which is LaTeX. And here, this is %g because I'm replacing x with a, or this placeholder here with a number. So here here I'm saying sim.latex to get LaTeX code. LaTeX code here, this is literally just a number as the result of substitution. Okay, and then we see what that looks like here. In exercise 5, you will continue working with SymPy to demonstrate two properties of differentiation. One property is scalar multiplication, and the other property is addition. And so together we call these the linear properties of differentiation. So to start with, there's another part of the experiment that I will get to in a moment. But to start with, you want to implement two different expressions or different differentiations. First, define the function alpha x squared plus beta cosine squared. So that is one function where x is a symbolic variable and alpha and beta are arbitrary constants. So they can be the number 16 or the square root of 42, whatever. And then you want to differentiate in SymPy that entire expression. So it's going to look like this. So one call to sim.diff to differentiate this function. And then what you want to do is break this up into 1, 2, 3, 4 pieces, right? So we have alpha, this constant, times the derivative of x squared plus beta, which is a separate constant, times the derivative of cosine squared. Okay, so we're breaking up the differentiation by these two terms, and then we are pulling out the scalar multiples outside of the differentiation operator. Now, when you differentiate both of those expressions, you should get exactly the same results because that is given by the linearity of differentiation. Okay, so let's see, there's more to do. There's the next part to this experiment. But first, I'll switch to Python and show you the solution to this first part. So here I am getting 4 symbols from SymPy: x to use as our variable, alpha, beta, and gamma. Actually, gamma comes in later on in this exercise, but I'm just getting it now. Okay, and notice also that there's a difference between how I am calling these variables in sim.symbols versus how I'm calling them as Python variables. So x is the same as x, but here I'm calling a symbolic variable alpha, but here I'm just calling it a. Now, the idea is that this a is a Python variable. This is a reference to what SymPy is representing as alpha. And then because I've spelled it in this particular way, SymPy is going to know that this corresponds to the Greek letter alpha. Same with beta, same with gamma, and you'll see gamma come in later in the exercise. Okay, so here's version 1. Notice I'm building up the entire function inside one call to sim.diff. So alpha times x squared plus beta times cos squared. And then here's version 2. Here, notice that I'm calling sim.diff twice. And I'm also pulling out the constant. So alpha times the derivative of x squared plus beta times the derivative of cos squared. And yeah, as I mentioned a moment ago, if the universe is kind to us, and if differentiation really is a linear operator, then these two results, V1 and V2, should be exactly the same. And no surprise, they are. Now, just to be clear, this is not a rigorous proof of the linearity of differentiation. I showed a proof in the text for this chapter that is more rigorous. This is a useful demonstration that will, first of all, help you improve your SymPy math coding skills in Python. And secondly, provide what I think is an intuitive and compelling demonstration of the linearity property. Now for the next part of this exercise. So here what you want to do is create a symbolic expression for this function, alpha times x squared plus beta times x cubed plus gamma times e to the 2x. And again, x is a variable. Alpha, beta, and gamma are just some arbitrary constants. Okay, so you can just implement this as one expression, so one line of code, one SymPy variable for this function. Then you can use sim.diff to calculate the derivative of this entire function. So far, nothing new for you to do. And then here comes the new stuff. Figure out how to separate this expression into separate variables corresponding to each term of this function. So you want to have 3 separate variables, 3 separate terms for the alpha x squared, a separate one for beta x cubed, and a separate one for gamma times e to the 2x. Now, of course, you could write this out manually, but that's not what I want you to do. What I want you to do is figure out how to get SymPy to recognize that this is one term, it's separate from this term, and it's separate from this term. So you can extract the different added terms from a multi-term expression. So that's what you want to do. Once you get that, then you can write a for loop, differentiate each term individually, and then print out that result. So your output of SymPy will look something like this. Here we have the derivative of the entire function. Here's the derivative of the derivatives of each individual pieces. And then inside this for loop, you can add all of these individual terms together and then print out the result here. Now, no surprise, this result is going to equal this result. This again follows from the linearity of differentiation. And the key point here is really to learn more about working with expressions in SymPy. So here I define one function to comprise these 3 terms. So alpha x squared, beta x cubed, and gamma times e to the 2x. Okay, and then I print out the derivative of that function here. And here I'm looping over. This is fun.args. Okay, so .args is the property of this function, this SymPy variable, that will return different arguments for each piece. And actually, let me just show you that. I think I will comment all of this out, and here I will write fun just to show you this function. And then I will write fun.args, and that is going to give us a tuple with 3 elements, and it's 1 element for each of the additive terms in the expression. Okay, so just to illustrate this a bit more, I think I'll just comment this out just to make this simple. So now there's only 2 terms, and now fun.arg is just going to contain those 2 terms. All right, back to what I had before. Okay, so now I'm looping over all of those arguments, individual arguments, displaying each argument in this variable called piece, and then differentiating that piece. And then I'm adding that piece to what I call variable combined, which is just pooling all of the, or amalgamating all of the individual terms, which I then print out here. Okay, so that is, I start by initializing this to be an empty string, and then I'm just concatenating more LaTeX code onto this piece. So we can run that code, and that reproduces the text that I showed the screenshot of in the book. Welcome to exercise 6 of chapter 5. The purpose of this exercise is to implement 2 algorithms in Python. One algorithm will allow you to calculate a secant line, and the other will calculate a tangent line. And together, that will allow you to recreate this figure. This was figure 5.7 in the text. And here I illustrate a tangent line here and a secant line going through these 2 points of the function x squared. So now let me tell you about that algorithm. So the algorithm looks like 6 steps. First, you want to define the function and its derivative, and you can do these using regular Python functions, so with the def keyword, or as lambda expressions. And then you need to define the x-axis intersection points, so you can pick 1 point for the tangent line because the tangent line intersects the function at 1 point, and 2 points for the secant line because the secant line intersects the function at 2 points. Here I refer to these as x sub t for the tangent line, and x sub s1 and x s2. Okay, and then you need to calculate the corresponding function values. So you have x sub t and f of x sub t. And same thing for x of s1 and x sub s2. Then you need to calculate 2 slopes. So the slope for the secant line and the slope for the tangent line. The slope for the secant line is the familiar slope function, so it's delta y over delta x. In this case, that is the change in the function values between xs2 and xs1 minus the change in x values. Okay, and then for the tangent, the slope, of course, is the derivative at that point. So this is the slope of the tangent function at point x sub t. And then almost finally, you want to write a function to calculate the line values. So this is for drawing the actual tangent line and the secant line. So far, all we've done is calculate the points on the function and the slope of the line. And now here you want to write the function. Okay, so this is a Python function that will return y sub s for the expression m sub s, which is the slope of the secant line, times x, basically x shifted by x s1, plus y of s1. Okay, so I hope this makes sense. We are basically defining a new line where the slope of the line is the slope of the tangent line, the secant line. Here's the x. We shift the x according to the location of the secant line and the intercept term. Okay, and then, so this is the function for the secant line, and then we have another Python function for the tangent line, which is essentially the same, except the slope term and the x and the y terms are different. And then the final point is not actually about the algorithm, but it's about generating the plot to show the function, in this case, x squared, and the tangent line and the secant line. And that reproduces figure 5.7 that I showed at the beginning of this video. Here is where I define the function x squared and the derivative 2x. And I chose to implement these as regular Python functions. You can also use lambda expressions if you like. Here are the three x-axis points. The tangent line will intersect the function at x equals 1.5. And the secant line intersects the function at x equals -1 and x equals 3. Now, these are not the function values. These are the x-axis values. To find the corresponding function values, we need to use or to call this function here, f of x, using these x-axis points that I've defined here. Okay, so now we have the x and y coordinates of all the points. Here I define the x-axis grid, and then we need to calculate the slope. This is the slope of the secant line. It's the change in y divided by the change in x. And here is the slope for the tangent line, which is literally just the function derivative at that point. Okay, and then here's where I have a separate function for the defining the points of the secant line. This is the slope times x plus the y-axis intercept, and then the function for the tangent line. And I guess, now that I'm looking at this, these two are basically the same. So if you want, you could actually implement these as one Python function, but then you have to take in as input the x values and also the x shift values and the slope and the y term. So in fact, maybe you don't even need these to be separate Python functions. But anyway, multiple correct ways to solve this problem. As long as your code correctly implements the math, it's all good. Lots of variety. Okay, so then the rest of this is just plotting. Here I'm plotting the function. Here I plot the secant line. You can see I'm plotting x by the function secant line and x by the function tangent line. This is going to return the y-axis values here for plotting these two lines. Okay, and then here I'm just plotting little circles at the intersection points. Okay, very nice. This reproduces figure 5.7 in the book. I hope you found this explanation of the algorithm for calculating the secant and the tangent lines to be insightful and to help you understand the distinction between tangent and secant lines. Exercise 7 is not too difficult. You will use SymPy to repeatedly differentiate a polynomial. In particular, you start with the function f of x equals x to the power of 10, and then calculate its derivative. Now, we don't need SymPy to do that. We can just do that in our heads. Of course, you know the rule for differentiating powers. You take this exponent, you bring it down as a multiplying coefficient, and then knock this down by 1. So the derivative of x to the power of 10 is 10 times x to the power of 9. And then the second derivative, so the derivative of the derivative is going to be 90 times x to the power of 8, and then so on. So you take the derivative of the derivative of the derivative of the derivative repeatedly, and you keep going through this 10 times. Eventually, you will get just a scalar. You're just going to get a number. Now, if you were to differentiate this scalar an 11th time, so starting from differentiating x to the power of 10, an 11th time, then you would get 0. So basically, with any polynomial, if you keep taking the derivative, eventually you will get a derivative of 0. Now, it might take a while. If you have like a term that's like x to the power of 10 billion, it's going to take 10 billion plus 1 derivatives to get down to a derivative of 0. But ultimately, every polynomial will eventually differentiate to 0 if you keep differentiating over and over and over again. That becomes relevant for some concepts you will learn later in this book, for example, L'Hopital's rule. Okay, so yeah, basically you want to create an output in SymPy that looks like this. So we start with the function and then differentiate it. And now the function becomes the derivative and then differentiate it. And then the new function becomes that derivative and so on. So here you can see I'm starting with the function x to the power of 10. And then in a for loop, I am differentiating that function. So I get this variable df, the derivative of f, printing that out, and then updating the function. So updating this variable so that the new variable fx is df. And then I differentiate that again. And so on, not quite ad nauseum, but we keep going through 10 times, and then we get to this function here. And actually, you can play around with this. You can set this to be 11, and then you'll see the derivative is 0. And of course, once we get here, you can keep taking the derivative over and over again, and you're just going to keep getting derivative of 0 because you just get a function of 0. Here in exercise 8 of chapter 5, we are going to explore approximating the derivative using numerical differences in NumPy. So here's what you want to do. Start by implementing the function f of x equals x to the power of 4. And you want to implement this in NumPy, not in SymPy, because we are going to work with numerical calculations, not symbolic, exact differentiation. Okay, so compute the empirical derivative using numpy.diff of your function x to the power of 4. And then you want to calculate the second derivative by taking the first derivative of the derivative, right? So I hope that makes sense. So you have one variable for the function, and then you want to create a second variable, again in NumPy, as numpy.diff of this function, and then you create a third variable, and that variable is the derivative, so numpy.diff of the output of the numpy.diff function that you applied to the original function. Okay, you keep doing that again and again and again until you reach the third derivative, and then plot the original and the three numerical differences as in this figure here. So here in the black line, you see x to the power of 4, and then the first derivative, the second derivative, and the third derivative. Now, the third derivative here is a straight line. It's a linear function. And, well, of course, you know why that's the case. And you also demonstrated that in the previous exercise analytically in SymPy. Now, when you are working through this exercise on your own, make sure to pay attention to the y-axis values. And your y-axis values should match the y-axis values that you see in this figure here. If they don't match, then think carefully about how you are scaling each derivative by dx, by delta x. So that is the first part of this exercise. There's another part of this exercise that I will discuss after first showing you the code and creating this figure. Here I define the x-axis grid, and here I create dx, variable dx. Now, sometimes I define the variable dx to be the second point in x minus the first point in x. Here I'm calculating it as the derivative of x, and then the average of all of those derivative points. Those are equivalent. You can use either method. Okay, here I have the function f to the power of 4. Here I take the derivative, or the numerical difference, of the original function, divide by dx. Here I take numpy.diff again, but now this is not of the original function, it's of the first derivative. And then again, I have ddf, and that is the derivative of this derivative, which is the derivative of this, which is the derivative of the original function. Now, notice that each time I'm calling numpy.diff, I have to divide again by dx. So we keep having to normalize by dx over and over and over again each time we call numpy.diff. Okay, so first I'm going to show you that this recreates the plot that I showed in the book. So nothing terribly surprising there. If you accidentally forgot to continue scaling by dx, then basically you will see that the shape of all of these functions is correct, but the y-axis scaling is incorrect. Okay, so that is for the scaling. And then one other really minor point that I wanted to let you know about or mention here in just a little bit of LaTeX coding. So here I have slash comma, and that basically just inserts a little bit of space. So here you see the F, for example, the double prime. Now notice there's a little bit of space between the F and the asterisk here. If I get rid of this slash comma, then you see that there's less space here. You can compare this amount of space from the double prime to this amount of space for the single prime. In my humble opinion, it looks a little bit clearer when there is a little bit of a gap, a little bit of horizontal spacing. And that's why I prefer to put in this little bit of space, slash comma here. So that was the first part of this exercise. The second part of this exercise is basically to reproduce exactly this figure, but now instead of calling numpy.diff repeatedly on the output of the previous numpy.diff call, you are going to continue calling numpy.diff on the input function, but using an optional second input into the numpy.diff function, which is the order of the derivative. So this is the first order derivative. Here we have the second order derivative. So notice that I'm inputting f of x, here variable fx. So the original function, but the optional input 2 is going to give me the second derivative, or the numerical approximation of the second derivative of this function. Okay, so then basically this small change, just to give you some familiarity with working with numpy.diff and optional second inputs. And that is what you see in this code here. Now, almost all of this code cell is exactly identical to this code cell. The only thing I have changed is this here. So now I'm calling fx each time I'm calculating the higher order derivatives instead of calling or inputting, for example, df here. Okay, and then I have the optional second input here. The default is 1, so you could write numpy.diff fx comma 1. That's the default behavior. Okay, here's the only tricky part of this exercise. You have to call or scale by dx for as many times as you are calculating the higher order derivative. So this, for example, would be incorrectly scaling by dx here, right? So it needs to be scaling by a dx term for each higher order derivative. Okay, so that is a tricky point, something to keep in mind. Okay, and then, yeah, running this code just reproduces the plot again. Exercise 9 of chapter 5 is conceptually similar to exercise 8. So this is a great exercise to do after having already completed exercise 8. The main goal here is to reproduce this figure here. So what are we looking at here? Well, we see the function cosine of phi plotted in a domain of minus 1.5 pi to plus 1.5 pi, inclusive bounds on both sides, and using a resolution of delta phi equals 0.01. So sometimes I show code where you can specify the resolution in terms of the number of points between two particular intervals or within an interval. And here, what you have to do is specify the resolution. You specify the delta phi a priori, or if it helps, you can also think of this as delta x. It's just another variable name that I'm using here. You specify the resolution, and then whatever, however the number of points ends up working out is how it works out. Okay, so then what you want to do is calculate the derivative of cosine in NumPy. So again, you are not calculating this symbolically, analytically, exactly using the SymPy library. Instead, you want to approximate the numerical derivative of cosine using NumPy. And then we already know that the actual derivative, the analytic derivative of cosine, is minus sine. So basically, we are going to plot these three functions on top of each other. So the cosine function, the analytic derivative, which we know is the analytic derivative, which is the function minus the sine of phi, and then the numerical approximation or the empirical derivative of the cosine of phi. Okay, and if the numerical approximation is a close match to the analytic derivative that we know, then of course the gray line and the gray circles should overlap. Ideally, they should overlap perfectly, as I've discussed in earlier in the chapter and also in earlier exercises. You can see that there is some discrepancy here, right? This line is not passing through the exact center of this circle, but it's pretty close. All right, so that is the goal of this exercise. I will now switch to code and walk you through my solution. Here I define the x-axis resolution in terms of dx. I suppose I should have called this variable d phi for consistency with the math that I showed in the book. But anyway, these are all just arbitrary variable names. So dx equals 0.01. And now here, instead of using numpy.linspace, I'm using numpy.arange. And I'm going to go from minus 1.5 pi to plus 1.5 pi in steps of dx or d phi or delta phi. Now notice here that I'm actually specifying the upper bound to be plus dx. So 1.5 pi plus dx. Now the reason why we do that here when using the function numpy.arange is that numpy.arange is going to actually calculate a exclusive upper bound. So this value itself is not going to be included in the output of this function because this bound here that you specify is exclusive. So if you want an inclusive upper bound, then you have to add a little bit onto this, the upper bound, right? So now this upper bound that I'm specifying in the function as the second input is actually larger. It's beyond the interval boundary that the instructions specified. But because this is exclusive and I'm adding a dx with a stepwise of dx, then this is going to return a value of a vector with an upper bound of 1.5 times pi. I hope that makes sense. I think it's clear in the code than from my explanation right now. Okay, so anyway, here's the function cosine of phi, and here is the empirical derivative, the approximation of the derivative as numpy.diff fx and divided by dx. And again, maybe I should have called this f phi instead of fx, but whatever. Okay, and then plot the function, plot the derivative, and here I'm plotting minus the sine of phi. And here I'm just skipping every 20 data values. This is an arbitrary thing that I'm doing just to facilitate the visual interpretation of the plot. Okay, and then, yeah, you can see to get the x-axis ticks and labels to have the symbol pi, you just have to specify them manually. So here I'm specifying that the x ticks are minus pi over 2, and so on, and the labels are LaTeX values of minus pi over 2, and so on. Now, there is a couple of goals of this exercise. One is just to improve your math coding skills in NumPy and Matplotlib. Second is to reinforce the concept, which you empirically demonstrate right here, that the derivative of cosine is minus the sine. And a third goal is, again, just another reminder, like in the previous exercise, of the importance of scaling by dx. So if you accidentally forget to scale by dx, then the result is going to be accurate in terms of the shape, the overall shape, but the y-axis values are going to be incorrect because you are not scaling. Now here, this looks like a flat line. It's actually not a straight line. This really is minus the sine function. It's just that the values are so small at this y-axis scaling, it looks like it's a flat line. Here we are in exercise 10 of chapter 5. As the instruction states right off the bat, this one is easy. I designed this exercise just as a way to give you a little bit more practice with coding and differentiating in SymPy and printing out LaTeX formatted equations. I don't think you will really suffer too much working through this exercise. So the main goal is to reproduce this cyclic nature of the derivatives of trig functions. So start with the cosine of x in SymPy, and then differentiate the cosine of x. And of course, you know that the answer is going to be minus the sine of x. And then differentiate that and differentiate again and again and again until you get back to the cosine of x. And just print these out in SymPy. So if you want, you can actually copy paste code. But I do recommend, because this is not terribly difficult in terms of the calculus concepts, I recommend challenging yourself a little bit and writing the code completely from scratch for this exercise without looking back at any of the previous code from this chapter. Okay, so I will now scroll up and show you this figure, and then I'll switch to code so you can see what the solution looks like. So here is the figure I'm referring to, and basically, yeah, it's just saying that the derivative of cosine is minus the sine, the derivative of minus sine is minus cosine, blah, 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 until we get back to the cosine. Here you see that there isn't a whole lot of code that we need to solve this exercise. Here I'm defining a symbolic variable, initializing the this variable f to be the sympy.cosine of x. Again, remember to use sim.cos and not numpy.cos. And then here I'm just cycling through. So over 4 iterations, I print out that the function derivative is the derivative of the function calculated in SymPy. And then I overwrite f. So I update this variable f to be the derivative of the function, which then is differentiated again. Okay, and so if you like, so it turns out I actually didn't use any LaTeX coding to solve this exercise. But if you like, you could actually make this output look a little bit nicer by translating this into LaTeX code and using the function pair display and math to print out the LaTeX code of all of this instead of just printing it out as regular ASCII characters. The goal of exercise 11 is just to have a little bit of fun. This is a bit of a lighthearted, I hope you will find this enjoyable exercise, and basically just, give you a little bit more experience coding with NumPy and visualizing in Matplotlib. So here you see 2 functions, f of x and g of x. F of x is a, this is a scalar, I'll talk about this in a moment, times the natural log of the absolute value of x, and g of x is the natural log of the absolute value of x plus b. Okay, so a and b are just parameters. These are scalars, and they vary between -1 and +3 in 31 linearly spaced steps. So in a for loop, you want to vary these 2 parameters, a and b, and basically just draw each line of the function as a separate line in the figure and using a separate grayscale value. Now, I try to make most of these figures in grayscale for the book, so the book can be printed in grayscale. Obviously, you could plot these in color if you like. Okay, so here in panel A, we see a times the natural log of the absolute value of x. And again, each of these lines in here corresponds to 31 distinct values of a in the same range of x. Now, of course, the natural log function is not defined for non-positive values, but the function specifies the absolute value of x. So that means that the domain of these functions can include negative values of x. Okay, so here is panel A for function g. Here is panel B for function function g. And then here in panel C, we have f of x by g of x. So now notice x is not plotted on any of the axes. It's implicitly drawn. And instead, we have the function values f of x on the x-axis, and the y-axis is the function values for g of x. So I call this function pretty logs because yeah, it's log functions, and I think the graph looks nice. Okay, so here is where I specify the numerical values of x. Here is the values for a and b, so 31 steps between -1 and 3. And this is where I define the color values. So it's going to range from 0 to zero point 0.8. These are the grayscale values in length of A and B, which is 31. Okay, so here I have a for loop. I'm looping over the colors and the A and B parameters. Here is where I'm plotting into panel A. I'm plotting, here I call this variable I, but this is actually A. The natural log of, so A times the log of the absolute value of X. Here is the natural log of the absolute value of X plus B. This is what I call the parameter B in the book. And then here I have the function f of x by the function g of x. Okay, now if you like, it would be perfectly acceptable to have your code look like this. So here you define f and here you define g as separate variables. And, that would look something like this. So this would be for f. And now here you would plot f and here you would also plot f. If your code looks something like that, that's great. There are many correct ways to solve these exercises. And I do not want you to think that the way that I happen to do it is the only solution or even the best solution. Okay, so all that said, yeah, here's what the function looks like. You get a bunch of warning messages. These are not errors. These are warnings. These are not Python errors. These are not coding mistakes. These are math errors because we are dividing by 0. So perhaps you can look into this warning message, look into this function, look into the values that I used here and figure out where this warning comes from, why we're getting it, and how to prevent that warning message from being printed out. Okay, all that said, I hope you enjoyed this exercise. I think these graphs look nice. And yeah, this one in particular looks pretty wacky.